We are going to start a new video series about mixed designs. In the previous video series, you've learned about between subjects factor designs, and you have learned about within subject factors designs. So you can probably guess that a mixed design includes both between and within subject factors. That's indeed the case. So we're going to start with reviewing between subject factors, and then in the next video, we're going to look at within subject factors, and then we're going to put it all together for a mixed design. A word of caution as we get started. There is something in analysis of quantitative data that is referred to as a mixed effects analysis. And mixed effects is not the same as a mixed design. Sometimes it's called mixed effects designs, so it can get especially confusing. Mixed effects is a topic that I cover in a more advanced class. It basically involves both fixed factors or fixed effects and random effects. And in this, we're looking at between and within subject, which is a different thing. So just be aware that when you're reading the research literature or you're reading about statistical analysis, that when you see the term mixed, you better be clear about whether it's talking about mixed effects or whether it's talking about between and within subject factors, so you'll have to consider context. I'm sorry that it is so confusing. I didn't invent this. But there you have it. Mixed effects is pretty common, as are mixed designs. We're going to be looking at mixed designs in this video series, beginning with between subjects factors. So let's take a look at that first. The key element of between subject factors is that each unit is measured at only one level of the factor. I'm going to refer back to what I did in previous videos with between subjects factors. Here I have an example in which we looked at the perception of airplane risk for 3 worldviews. So if you look down at our first graph, figure 1 here, that we created when we were going through between subject factors, you'll see that we have 3 box plots indicating 3 different categories of a single between subjects categorical variable worldviews. What makes it between subjects is that each participant in our study is in one and only one category. So everyone that went into making up this first box plot here of individualist was not in the other 2 categories. They were only categorized as individualist. Similarly, everyone in hierarchicalist is only in hierarchicalist, and everyone in egalitarian is only in egalitarian. We have a single factor, worldviews. That factor has 3 different levels or categories, individualist, hierarchicalist, and egalitarian, and every single participant in our study is categorized as being primarily in one and only one of these categories. So that's what makes this a between subjects factor. When we're analyzing between subjects factors and looking at the effects, what we're looking at are differences in the centers of the distribution of each category of the factor. And we can estimate that effect in an omnibus fashion by comparing the variability between groups, that is, how much difference is there from group to group to group, to the variance within groups. Returning to those box plots, you can see the variability between the group centers by looking at these lines. These are medians, or descriptively, we can look at medians or means to look at the differences in centers of the distribution, and we can visually see a difference in centers here in which individualist and hierarchicalist are similar to one another but different than egalitarian, and we also see that here with the means, that the individualist and hierarchicalist mean are within a couple points of each other, but over 10 points different than that in egalitarian. So that's the variability between groups. The variability within groups can be seen in the actual range of the data itself, both in terms of the full range and the interquartile range, looking at how participants within a particular category vary from one another. We can also see this intra-group variability, this within-group variability, by looking at the standard deviations for individualist, hierarchicalist, and egalitarian. When we're estimating the effects of a between-subject factor, we compare the variability between the groups to the variance within groups. Why do we do that? Well, we know that if we were to take another sample, we're going to get different results. So the question becomes this: when you get these differences between groups, are those differences just a function of the sampling variability, or are they a function of a real difference that we would exhibit even if we had all the population data available to us? The fact is, we're going to get differences between groups regardless of whether there are actual differences in the population, simply because we're drawing samples. And if you draw different samples, you're going to get different variances of the means. But the amount of variation that you get between means should be very similar to the amount of variation that you get within groups. That is, if we were to look at our analysis of variance table that we created down here, the variance that you see exhibited here in the mean square for view should be similar to the variance we see here in residuals if there is no group effect. Because the variance we see between groups is always going to be a combination of the actual between group variation plus the random variation from sampling, that is, the variation that we see similar to within groups. So here, the fact that we have a value that is 6 times, you can see that in the F ratio, about 6 times as large for the different worldviews than it is for residuals, tells me that I probably have variation that I can infer beyond just this particular sample, variation of means, because this variation here of worldview, these different groups that we saw up here, the variation across these groups relative to the variation within groups is quite high. So effects are measured by comparing the variance between groups to the variance within groups. Now, we can measure those effects descriptively, but ultimately we may want to know, we probably will want to know, if we can make inferences outside of this study. And in order to do that, we're going to have some conditions for valid inference. One is that we have independence of units within a factor. Another is we have independence of units across the levels of a factor. That independence of units across the levels of a factor is what really defines between subject factors. So looking again at our box plots here, everyone who goes into making up this particular box plot for individual has to be independent of everyone else within that same box plot, but also has to be independent of the individuals that make up the box plot here for hierarchicalist. So you have independence of units within a factor and independence of units across levels of a factor. You also need homogeneity of variance of our residuals. The reason that's true is because when we go down here to our ANOVA table, we are using a single estimate of the variation within conditions. But we have 3 conditions here. We have 3 conditions, but if the variation is similar within all of those conditions, then we can pool the data together and get a single estimate, as we're doing here, this particular mean square, of 666 is our single estimate of the variance within conditions. This is pictured in this plot right here, this residual versus fit plot among the three groups, in which we're looking at the variation of the first group, the variation of the second group, and the variation of the third group, and those variances should be similar. Back up here, we see fairly similar standard deviations. Squaring those would give us our variances, and people use different rules of thumb about how close is close enough. The most common rule of thumb probably is if the largest variance is no more than 4 times the smallest variance, you're probably okay to use this single number as a single best estimate of the variation within each of those conditions. So that's a one number estimate for 3 different estimates, the variance within each of the conditions, which is why we need that assumption of homogeneity of variance of residuals. We also expect our residuals to follow a normal distribution in order to make valid inferences. And so if I look back here at our QQ plot, I see that I have actually higher sample quantiles on the end in the positive direction and higher sample quantiles negative, that is higher absolute values, in the negative direction. And this kind of pattern is what we would expect to see when we have some positively skewed data. So it's not quite normal. The good news is that if you have a large sample size, there is going to be normality of your variance estimates. There is going to be normality in terms of the sampling distribution. I said variance estimate, I mean estimates of statistics. The statistics in this case are the means, so not the variances. But whatever the statistic is, if you're going to have a big sample, you're going to probably have normality of the sampling distribution by the central limit theorem. That does not account for if we have unequal variances. Fortunately, here they were fairly equal. But it can account for lack of normality. So the fact that we have a little bit of right skew, and by the way, I think we can see these even in the box plots, that if you look at these box plots where the medians occur and then look in the positive direction, the upward direction, you see these are spread out a little bit more in above the median than they are below the median, and there's where our little bit of skew is coming from that we exhibit in this QQ plot. But in this particular case, given the sample size that I have here, I forget exactly what the sample size was. I'm looking down here at my degrees of freedom. It appears the sample size was 225. I know because I have 222 plus 2 plus 1. So I have 225 is my sample size, which is fairly large. And so therefore my sampling distributions are going to be normal even if my original population scores are not normal. So we need those 4 conditions in order to make valid inferences. What do we mean by valid inferences? We mean that when we set our probability levels for our rejection of the null hypothesis, that is our maximum type 1 error rate, that we expect that's actually the maximum type 1 error rate we're using, not some unknown value. If we do not meet the assumptions for valid inference, we could be rejecting more times or less times than we had anticipated when we set our type 1 error rate, and also when we set our confidence interval levels of confidence. So in this particular case, because of my sample size and because of homogeneity of variance, and because I have met the independence assumption, which, by the way, is a function of our design, not our statistics, I believe that I can make reasonable validity statements about my inferences that I'm making in this particular study. Examples of between subjects designs, we've looked at 2 of them. The completely randomized one-way design, or another example would be the one-way design, and that's actually what we have here. Notice I've removed the words completely randomized. Why is that? Because in order to put people into different categories in terms of their worldviews, we did not randomly assign them. We, in fact, just measured them. We gave them an instrument. And after looking at the scores and how they answered the items on the instrument, we identified them as being individualist, hierarchicalist, or egalitarian. So while a completely randomized one-factor design is a between subjects factor example, so is non-randomized one-factor design as long as individuals are placed in one and only one category. Another example that we have is a two-way design, and that could again be completely randomized, or it could be randomized on one factor and not the other, or on neither factor. Let's look at the example that we looked at in a past video series for the two-way design. That was this study, the effect of vitamin C on guinea pig odontoblast development as a function of delivery method, orange juice or direct vitamin C, and the dosage. And so we looked at plots like this to look not only at the effects, noting that orange juice was better than vitamin C in terms of odontoblast growth unless we had high dosage, in which it didn't make a difference. We looked at this as an example of a two-factor design. If I go back up to these box plots, we have 1, 2, 3, 4, 5, 6 of them. And again, for a between subjects factor, it means that each guinea pig was put in one and only one condition. Now, in this case, it was indeed a completely randomized design, because when those guinea pigs were put in conditions, they were randomized on the basis of what dosage they were going to get, as well as on the basis of what delivery method they were going to get. Every guinea pig in each box plot is in one and only one box plot, does not appear in the others. So this again is an example of a between subjects factor. So remember, we're leading up towards a mixed design in which we're going to have one factor that's between subjects. So you now know that for that factor, individuals are going to appear in one and only one level. But we're also going to have in the mixed design a within subjects factor. So we'll review that in the next video.